Hey everyone, my name is Iwo Plaza, and I recently gave a talk at Render Atlanta 2025. And I wanted to record it as a video form for those that weren't able to make it. The title of my presentation is Your GPU is a JavaScript runtime asterisk. And what that asterisk means, I'm going to have to explain as I go along. So as I said, my name is Iwo Plaza. I'm a software engineer at Software Mention, and today I'm going to be talking about a library that we're working on called TypeGPU. And to give you a bit of a background on TypeGPU, I first have to explain a bit about our company. So I work for Software Mention. It's a software agency where you can come to us, and we create a top-shelf React Native app for you. We do a lot of the ecosystem contributions. So Software Mention created and is maintaining React Native Reanimated, React Native Gesture Handler. TypeGPU is now one of those libraries that we can use to make your apps stand out and be highly efficient. I came to Software Mention with the idea of TypeGPU like a year ago, and they said, "Okay, cool. Here's a team, here's resources, and you can work on this full time." So I'm very grateful to Software Mention for giving me this opportunity. It's been really amazing, and I want to really share what we've been working on for the whole year. And on the side, I just like to make small games and draw and make music. So, JavaScript, our favorite language. Recently, because of a new standard called WebGPU, we're able to access our graphics cards pretty much directly. We're able to send data and instructions to it. We're able to get data back, and it happens asynchronously. It's basically a separate process that we can talk to and tell what to do and get results of our computation back. And of course, it can be used for 3D rendering, what GPUs were historically made for, but also for local AI inference, physics simulation, basically any highly parallelizable task. So that's awesome. But what about those instructions? What language do we actually send them in? Well, it's a special language. It's a new language called WebGPU Shading Language, in short, WGSL. And it looks a bit like this. It kind of looks like Rust, but for most JavaScript developers, it's going to look like this. So to actually send the instructions over to the GPU, we have to basically write them in a string or import them from a separate file and hand them over to WebGPU so that it can compile them to a lower level form, like bytecode or the native code that the GPU can actually execute. That DX is not really that great, right? We don't get syntax highlighting or anything, but that's what we get. So about this asterisk, the actual title of my talk is actually Compiling JavaScript to WGSL and the Quest for Type-Safe and Composable WebGPU Libraries. I'm actually going to try to convince you today that writing shaders in JavaScript is actually a great idea. The highly single-threaded and interpreted language, untyped language. Hopefully by the end of this talk, you'll understand where I'm coming from, and hopefully you'll be as excited as I am for the prospect. So let's first imagine a scenario. We have two libraries created and maintained by different teams. One of them is ABCGen, used for procedural terrain generation. So you can use it for a game, let's say like Minecraft that you're building. And then we have another library called XYZplot. That's sole responsibility is just receiving some 3D data and plotting it on the screen so that we can visualize it and see what's going on with a data set. I feel like that's pretty reasonable for those two libraries to have those use cases and focus on them, right? The APIs could look like this. We have a generate height map function that takes in the 2D size of the grid, and it returns a height map. So for every cell in that 2D grid, we get a height value of that terrain at that point. And then we can plot the result in 3D space. We can initialize XYZ, tell it to draw that terrain. But what do we get? We get something that we can't really understand. No runtime error, nothing. So what's the problem? The problem is that, let's turn TypeScript on and let it tell us what's the problem. So terrain is actually a 2D array of number, and XYZplot accepts an array of 3D points, right? An array of tuple of 3 numbers. And I feel like that's a reasonable API for both of these libraries, but that they're incompatible. We have to somehow make them compatible. But we kind of know how to do that, right? As TypeScript developers, we can create a new array, index into the old array. I'm normalizing the data a bit, so it's better for visualization. So it's still the same data, but it's kind of in a different format. And yeah, we're just scaling it up to see more detail. And it looks a bit like this. I actually have a working demo of it that I can showcase. So let's get out of the slides for a bit. And okay, I mean, it looks great, right? Let's change the parameters a bit. So we can change the size of the terrain that we're generating. That looks great. But it's really slow. Like if I change it now, it takes more than a second to generate the new terrain and show it to us. So does it actually take that long? Let's kind of try to take it apart a bit. So we have our app. We have the two libraries, ABCGen and XYZplot. And then we have that line that signifies having to communicate with this GPU. And then, yeah, the GPU can draw onto a canvas to show the result. So what's the actual process? Well, we tell ABCGen to generate the terrain. So it tells the GPU, hey, well, I want to generate some terrain in parallel, right? That's reasonable. Okay, cool. The GPU says, cool, 8 milliseconds. I can do that really fast. So here you go. And actually pulling it back from the GPU to JS takes 125 milliseconds. That's way over budget for real-time applications. The budget for real-time applications is like 16 milliseconds. So that's like 10 times more than that. So we're already really slow. So, okay, well, ABCGen gives us the data back. Then we have to process it. So we have to change the form of it so that it matches the input of the next library. And that takes 400 milliseconds, half a second. That's terrible. Okay, we can pass that to XYZplot, and then it passes it on to the GPU again, which takes 650 milliseconds. That's terrible. And then the GPU can finally draw it, right? So what can we do about this? Like the actual work, what we wanted to do, which is generate and draw the terrain, takes about 8 milliseconds on my machine. But we're wasting more than a second of time just like changing the form of the data and pushing data back and forth between VRAM and RAM, like video memory and our memory, that the CPU has access to. So can we change that? I mean, yeah. Let's try to take a different approach. So we can tell the GPU, or the library can tell the GPU to generate that terrain. That's the same. But instead of actually pulling that data back, we can pull a pointer to that memory, right? We can ask the GPU to give us the pointer of that, where that data lives in the memory of the GPU, and then we can kind of just like move it around and do stuff with it without actually having to pull all that data back to JS. So yeah, ABCGen can give us that pointer back, and then we can tell the GPU, hey, this data that you're holding, run this program on it, written in WebGPU shading language, and turn the data into a different form so that it matches the input of the next library. And then we can just pass the pointer to the next library. And it can, tell, hey, GPU, draw this data that's already in your memory onto the screen. And with this setup, the actual work is 8 milliseconds, and the time of trying to interrupt between those two libraries is just 5 milliseconds. That's actually pretty fast. So let's see the demo. I mean, we have the second version, which is the GPU. And if we change the slider, it's instant, right? It just, it generates it instantly. So let's go back to the slides. Okay. Well, what's the problem? Are we done here? Not really. This is the API. This is what the API would have to look like. So the first library, well, it has to return that pointer, and that pointer is just GPU buffer, right? What's in that buffer? Not really sure. It's just a pointer to memory, right? If you're familiar with C or C++, it's basically a void pointer. It's some location in memory. We don't know what's in it. And then, we can pass it to the next library. That's fine, but we still have the same problem where the data format doesn't match between the output of one library and the input of another. And the type system, TypeScript, doesn't tell us the problem anymore. Both are locations in memory, so it's all good. But it's not all good. to actually transform the data, we have to write this amount of code. Now, you don't have to read into this, but just know that, this is what you would have to write as a user trying to consume both libraries at once. And that's not ideal. So we're kind of, stuck between two worlds here. We have TypeScript, where if we want to interop those two libraries in TypeScript, we require a memory transfer. It's slow at processing big data. It integrates well into your apps, though, and you can just create a variable and use it, and you don't have to worry about memory management. Well, in WebGPU, you can do stuff really fast, but you have untyped code. You're writing stuff in a string, and even though the code is typed in this little bubble, interoping with it is not type-safe at all. And you're sending binary blobs back and forth. The user is actually responsible for serializing and deserializing data if they want to actually interact with it. So what if we just, shuffle some things around, connect some words together? What if we could just create one library that does it all, and have all the bad characteristics shoved into some other project, web script or something? So this is what TypeGPU is aiming to solve. It's a shared layer between libraries. It improves APIs without compromising efficiency, and it simplifies library internals. So let's take a step back and see how those APIs of those two libraries would look like if they were written in TypeGPU instead. There we go. I'll take a little sip. But you can see that the buffers are not raw pointers anymore. They're actually well typed. We have a buffer of an array of F32. So that tells us that it's a double array of floating point numbers. So I feel like that's pretty clear. And then we have another API that accepts a buffer of an array of 3D points. I feel like that's also, that's the parallel of what we had in TypeScript before. And that's actually the internal representation of that data in memory. And, TypeScript would be able to tell us, hey, these two buffers don't really match each other. What are you trying to do here? So we have that safety where if one library returns some sort of data and another library consumes it, we're able to verify that as a build step. So I feel like that's pretty cool. But okay, we have an error. That's awesome. How do we actually solve this error now that we know it's there? Well, we can actually just create a new array, just like we were doing in TypeScript. But in this case, we were just allocating memory on the GPU with a specific type, which in this case is an array of vec3, 3D points. And the length of this array is size times size. So it's a 2D grid, size by size. And then instead of using this old buffer, we can just use this new buffer to draw. But it's empty right now. We just allocated some memory on the GPU. It's zeroed out. So we actually have to fill it with meaningful data. So let's say we have this helper function called dispatch2D. We can pass in the root, which in this case is just a typed wrapper around a GPU device, which we can use to interface with it. We can pass in how many threads we want to run in parallel. In this case, we want to run a 2D grid of threads. So it's going to look like this, basically. So for each cell in this grid, we're going to dispatch a thread that's going to call this user-provided callback, where X and Y are going to be replaced with the position of this cell in this imaginary grid. And we can mark that this callback is supposed to be running on the GPU with the kernel directive. So we just say quote kernel quote semicolon, and it tells TypeGPU that hey, this callback is supposed to be running on the GPU. So let's try to read terrain. Let's try to just read that buffer. To be able to read it, we have to get a read-only handle to it, and then we can just call terrain.value, index into it as if it was just a normal array, get a height value from it, create a new 3D point that represents that point in space. We can have just a scalar constant that we can declare outside of our shader and use inside of our shader, and it pulls that all in automatically. We just create a new point, map, just normalize it differently, scale it up the same as we were doing before, and save it back into our points buffer. This is the experience of actually writing it live. The IDE is able to actually suggest everything. It knows the data type of everything. So if you do train that value, it knows that it's a 2D array of number. And you can interface with it as if it was just a 2D array of number, even though this code will never run on the CPU. What you're writing here is just TypeScript that we're going to compile to WebGPU shading language for you and execute it on the GPU. And I feel like that's pretty cool. So it's not only, you can write this interop logic between those two libraries in TypeScript, but you also have, we're leveraging existing language tooling without having to create our own new language. And you can just hover over everything, and the language server tells you what the type of those variables are. So I feel like that's pretty cool. This is the result. We can just see the demo that it looks the same. There it is, TGSL, which is TypeGPU shading language, but it's, as I said, it's basically just TypeScript. There we go. It runs just as fast. Okay, let's get back into it. What is TypeGPU? It's auto-serialization. You define schemas, and we do the serialization and deserialization for you. You can write shaders in TypeScript, but you don't have to. We provide you full flexibility. You can write your shaders in whatever you want, WebGPU shading language or TypeScript. And you can let TypeGPU be just the outer layer of your library, or build your whole app or library from scratch in TypeGPU. And you can use TypeGPU today in libraries, in existing projects, or, as I said, in new projects. It's really easy to incorporate. And I feel like, TypeGPU, it's the goal, at least for us, is that we're able to reach a composability that our libraries deserve. On par with what TypeScript did for JavaScript, we kind of want to do the same for WebGPU. So, hope you made it this far and you understand kind of what our motivation is for it, and hopefully you're able to see why we did it in the first place, and you're as excited as I am about it. So now I'm going to try and explain how we do it. So in the simplest case, you can think of our typed buffers as just wrappers around the vanilla WebGPU buffers. So we're basically just a fat pointer. We house more information on the type level, not necessarily in the runtime level, but we do have some stuff that helps you with serialization and deserialization. So in this case, you can just create a new type if you are building your own type GPU, let's say, TGPU buffer, generic parameter, house a schema, and the raw pointer underneath. So you still always have access to this raw pointer if you want to just have direct WebGPU access. That's still fine. Just if we do that, TypeScript is already able to determine, hey, these two generic parameters don't match. But what do we actually put in those generic parameters? Well, we could put, let's say, just like regular JavaScript types, right? We could do number, array, and something accepts a tuple of numbers, and that's fine. But actually, in WebGPU, we have a distinction between numeric types. So F32 is not the same as I32 or U32. Each of them describes something else. Floating point number, signed integer, unsigned integer. So we want to be able to differentiate between them because they actually differ in memory, right? We want to protect users from that. So, we could just use string literals, right? That's fine. It's not perfect though, but it's a start. What do we actually do? Well, we create just new objects with a wrapper property on them, which is a little bit hidden. It's not as opaque as seen here. But you can use those and compose them together. And we can have more complex types like a WGSL array that accepts an element type. And the representation of that WGSL array is actually just the representation of its element type as an array, right? What that allows us to do is when we, I guess this would have a type error. So we're going to have base data that everything extends, and that's fine. But what that allows us to do is to be able to access the buffer's value on the GPU side in a type-safe way. So we can say that the value of this buffer is just the representation of its schema. And then if we have a buffer and we do foo.value, it's able to infer whatever custom user schema provided into a well-typed value type. So I feel like that's pretty cool. And yeah, you can use a technique to kind of hide the wrapper as we do under a symbol. And in that way, it's available on the type, but it's not accessible to the end user because it actually doesn't exist as a value in JS. It's just a type hint. How does it look like in practice? Well, we export a lot of functions that you can use to construct your own schemas, similar to Zod. And they house the information about their type on the type level, but also at runtime to aid in serialization. So what about TypeScript? Being able to compile TypeScript to WebGPU shading language, where, it sort of looks like this. We have a build plugin. Like right now, TypeScript doesn't run in the browser, so you have to first transform it into a final form of JavaScript that you can then run in the browser. And we can kind of hook into that process. A lot of bundlers allow for plugins, and we have our own plugin that allows you to write functions, and we do stuff to it. What do? Well, we take this form. If you define tgpu.fn and you provide the schema for its attributes and return type, we detect that and we take the callback, so the thing that you provide as the implementation of that function, and we turn it into an AST and compress it. And this format we call tiniest, which stands for Tiny Embeddable Syntax Tree. And ironically, the format you see is larger than what was there before, but it's way smaller than an abstract syntax tree would be. So this is very good for just embedding into your program, and we're able to, at runtime, very efficiently generate the final WGSL. So yeah, this happens at build time, and then at runtime, we take that representation, we take the shell, those argument types and the return type, and we're able to generate appropriate WGSL. And as you can see, it's really similar to what we had before. And the grid size, the constant that we used, is inlined into the final shader code. And we have a lot of examples that already use this functionality. You can go to typegpu.com and look at experimental live examples, and you're going to be able to see how we use it currently. And you also can just bootstrap your own projects by clicking Edit on StackBlitz. Check it out. You can see my slides and my GitHub. It should be pinned on my profile. The repository is called The Quest for Type-Safe WebGPU Libraries. And you can follow me on social media. And you think it's the end of the show, but it's not really. I want to do some live coding, but I gotta shuffle things around here. Okay. Let's see. So what I actually want to do is showcase what you can do with TypeGPU apart from just gluing libraries together. The actual API of libraries can become better and more customizable. And what do I mean by that? Let's look at the code. I'll make it bigger. Okay, there we go. I feel like that should be good enough. So yeah, you have this init xyz function that we use to create the plotting library. And it accepts, some configuration, and you could expect, okay, we can change the size of the points, right? So we can go point size 1. And how is that going to look like? That's going to overpower everything. But yeah, that's pretty thick. Yeah, I mean, you can see some stuff there happening, and I feel like that's reasonable. You can have a parameter, and we pass that to the shader. What's cool about that? Well, the library can do more. Actually, you can see that this API accepts a number or a function that accepts a position and returns a number. So how can we use that? Well, we can just pass in a callback here that accepts the position. We can mark it with the kernel directive. And for now, let's just return what we had there before. Does that still work? Yeah. But we can also just use the position to modulate the size. And let's do an absolute of that. We can import from the standard library and kind of see how that looks like. Yeah, that looks good. We can do a larger frequency. Yeah, that looks good. So what you're seeing here is this callback is not actually running in JavaScript. It's being compiled by TypeGPU into WebGPU shading language. So what else you can do? What else can you do? Well, you can do everything else. Position. Yeah, that looks pretty cool. Okay, well, we have another property, which is color. You can do the same. Get a position. And we can mark it as a kernel, so TypeGPU knows that it's supposed to run on the GPU. And we can return like the X position. Let's modulate it as well. Okay. And we can see that, there's a problem. It actually expects a callback that returns a 3D vector, not a number. Okay, cool, type safe. That's what we wanted. So let's create a new vector. We can do it like this, but we already imported, so we can just do it like this. And let's say it's modulating the red color. And yeah, there we go. It's partially red based on the X position. We can do it based on the Z position, and it's got stripes. And we can do just different colors and offset them a little bit, like this or like this. Yeah, it doesn't look too visually appealing, but you get the idea. Maybe this will be. Yeah, yeah. So that's what you can do. Thank you for listening to my live coding session, and thank you for listening to my presentation. I hope you're as excited as I am about this prospect, and see you around. I hope to do more talks like this. Thank you so much for watching. Check out TypeGPU today and let us know what you think.